So we can go ahead and get started. Welcome everyone again. My name is Carlton Fong, and along with Derek Rogers here, we are co-chairs of the Systematic Review of Meta-analysis SIG of AERA, and we are supported by the Dream Team from Georgia State University, and they are helping us run all of these webinars. And thanks to James, who was the former chair, who kind of helped co-organize this as well for the last few years. And we're excited to relaunch this this fall. And of course, we had to invite James for the first one, and we're really delighted that he's going to be sharing some of his recent work around a preliminary data analysis workflow for meta-analysis of dependent effect sizes. We think James will go for about 45 minutes, which will leave us about 15 minutes or so for questions and comments and discussion. And I know James is really open to hearing thoughts about how applied meta-analysts actually go about handling some of these thorny issues. And so we're excited to hear what James has to share, and we'll let him take it away.
Thanks, Carlton. Thanks a lot for guilting me into doing this. No, I mean inviting me to do this this webinar. It's a pleasure to be on the other side of the table here, and I'm excited to share this work. This is from a paper that's is I guess slowly like crawling towards the publication process. It's going to be in the Transactions of the Royal Society in a special issue on statistical workflows. What I present today is it's based on a paper that is co-authored with two of my favorite people, Jingru Zhang, who's a graduate student at UW-Madison, working with me. Jingru's on the call there. And Beth Tipton from Northwestern University. I did not list them as co-presenters because they had not seen the slides, but many of the good ideas in the paper are theirs. And if you want to see the full paper, I'm just going to give you kind of highlights today, but I've got a link to the full paper right there. I'll drop it in the chat as well. There we go. Okay. So I think we're probably pretty familiar with the process of doing a research synthesis. Here's the 7 steps as described by the Harris Cooper, right? Moving from problem formulation through searching and screening the literature, coding studies, assessing the quality of the evidence, and then doing statistical analysis of the quantitative findings, critical assessment, and reporting. Today, I want to zoom in on step 5, right? Synthesizing effect sizes. And, there's, of course, a ton written about this. Many textbooks and articles are focused just on this stage of the research synthesis process. But there's actually several things that happen in this stage. One way of characterizing them is to say, right, we start with doing, presumably, a preliminary analysis of the data that we have put so much effort into culling from the literature. By preliminary analysis, I mean things like data integrity checks, running basic descriptives, and using that information to try to make sense of your data. And I think that often happens prior to doing formal models. So what I call formal modeling is things like doing summary meta-analysis models, meta-regressions, moderator analysis, things like that. So today and in the paper, we zoom in on preliminary analysis. And one reason for that is we don't talk about it. We looked in writing the paper, we looked in a bunch of textbooks about the research synthesis process, and there's not a lot of instruction about what should happen or what does happen in this stage. So preliminary analysis is kind of a black box, at least as far as the scholarly record of published literature on how to do meta-analysis is concerned. Right? We don't talk about it enough, and so our goal here is really just to get some conversation going. And it's has struck me as odd for years that people don't talk about this. Eh, Part of the reason being, I'm sure that experienced reviewers, right, folks like some of you all on this call, like Terry and Carlton, and many others who have written textbooks on research synthesis, surely have pretty well-developed routines for doing preliminary analysis, right? If you work in a lab that does a lot of meta-analysis, you probably have pretty standard or established protocols. But what are they? They're not in the scholarly record. The other motivation here is I have the sense that less experienced reviewers, which includes many, many people who do meta-analysis. I think probably right, if you look at the published meta-analysis literature, the modal level of experience of the authors is pretty low, right? Many people are coming to do meta-analysis from being experts in a particular area and having to learn the methodology in order to do a review on a topic where they're really interested in the substance. And I think maybe in part because they're coming from different areas, I sort of have the sense that less experienced reviewers might not really devote enough attention to preliminary analysis. I get this sense from, say, from corresponding with people on like the RSIG meta-analysis listserv, or folks that reach out to me for advice about modeling. Oftentimes, I sort of have the sense that they haven't explored their data a whole lot. And so oftentimes the questions that I send back to them are about like basic descriptive things, right? Needing to understand that first in order to have a sense of what's an appropriate way to model their data. And in some senses, it's a little bit weird that there's not a lot of guidance about how to do preliminary analysis and meta-analysis in the area of research synthesis. There's been some activity in this realm in other areas of methodology, uh, thinking about how to sort of formalize the preliminary data analysis process and put more structure onto how data analysts engage with this stage of an investigation. I've included links here to some other work that looks at preliminary data analysis for, say, longitudinal studies or for observational studies to trying to isolate causal impacts. But there's really not much written for meta-analysis, as far as I know. A further complication here, and one of the reasons that we think that describing preliminary analysis workflows for meta-analysis, or is that it's necessary to do this for meta-analysis specifically, is meta-analysis data have special features. One prominent feature is in education and psychology and many other areas is that the data are kind of complicated because of the presence of dependent effect sizes. So dependent effect sizes occur, say, in studies where you've got uh, intervention studies where you've got a treatment control contrast, but there's more than one measure of the outcome that fits your construct criterion, or where you've got a measure of the outcome at multiple points in time, or if you've got an intervention study where there's more than one intervention condition compared to a common control condition. And as long as those multiple intervention conditions meet your inclusion criteria, right, there's reason to include both of them in a synthesis. But this creates some complexity to the data. Often, I guess the way I think about it is that, right, it puts hierarchical structure into the data. But of course, there's well-developed sort of formal methods for modeling dependent effect sizes. There's been a whole lot of work on this over the past 15 plus years. So here I'm thinking of methods like robust variance estimation, like multi-level meta-analysis models, combinations of those things, multivariate meta-analysis models. But what about the preliminary stages of the analysis? There's very little guidance at all, and much less guidance that's focused specifically on understanding these types of data structures. So that's what we set out to do in the paper. Thanks to Jingro, we have a fantastic acronym. So we call it the Preliminary Investigation of Meta-Analytic Databases, or PRIMED. So we talk about the primed workflow. And what we've tried to do here is just lay out some procedures for investigating the basic features and the features of your meta-analytic data that have to do with dependency, kind of focusing in stages from like sort of basic description more and more towards the variables that are going to be the key dependent variables in a formal model. So there's four stages. First, describing the amount of data and its dependent structure, like how much data do you have, how is it structured? Second, looking at study characteristics and potential moderating variables. Third, looking at the standard errors of effect sizes and other auxiliary data that's going to be used in the formal model, but isn't like the focal dependent variable. And fourth, looking at the effect size estimates themselves. So like the response variable, the dependent variable in the model. And we've structured it this way because we feel like this moving from sort of more basic description towards more stuff that's closer to formal inferential models makes sense as a workflow because it sort of moves from basic to technical. So what I'd like to do now is give you highlights of each of these stages of the workflow. And the highlights are just going to be things like, here is a useful descriptive table, or here is what we feel like is a good graphic visualization that gives you information about these features of the data. In illustrating this, in the paper we have a selection of different examples based on published meta-analysis work. Some of it from my own work, some of it from colleagues to whom we're very grateful. So today I'm going to use two different examples. One from a review of psychosocial interventions for adult cancer patients, looking at specifically outcomes that are measures of spiritual well-being. So this project was based on it's part of a big systematic review grant project. This paper was led by Laurie McCluth, and the focus is on really understanding the intervention effects, summarizing them, and then understanding how those effects vary as a function of a couple of different study characteristics. My second example comes from a meta-analysis of narrative assessments. So this is an interesting paper because it's looking at like just descriptive differences between kids with developmental language disorders and kids with typical development. So narrative assessments are a particular type of sort of cognitive tests that speech language pathologists might use to diagnose developmental language disorder. So understanding the differences or sort of how diagnostic different measures of narrative assessment are is sort of useful for informing practice. And so this is work that led by Katie Winters, who's now at the University of Cincinnati. The complexity in this review comes from many of the studies included had a bunch of different measures of narrative assessments. So there's a lot of dependence was really sort of a central feature of the data. So I'll use these two reviews and just illustrate some of the techniques from each of the stages of the workflow. Stage one, describe the amount of data and its dependent structure. It's really just what we mean is just counting, right? So answering questions about how much data do you have? What is the structure of the data with respect to the dependencies? And how big are the included studies? So for answering this, I mean, in answering these questions, there's a couple of pieces of information that we get from this, or a couple of reasons to look into this. One is just to verify that the database that you're working with is complete, that it's consistent with the inclusion criteria that you laid out at the start of the project. Another is that understanding how much data you have and the structure of the data gives us just sort of a initial sort of very hand-wavy sense of how precisely we're going to be able to learn about the distribution of effects. Right? So more studies means more precise estimates. And so more complexity means right, more complexity in figuring out an appropriate model for the data. So the last reason is right, understanding how much data you have and its structure is going to tell us something, at least initially, about what sorts of models you might need to use and how sensitive your analysis will be to the specific modeling assumptions you make. So here's one sort of simple descriptive from the Spiritual Well-Being Review. It's just a count of the number of studies by how many effect size estimates are included in each study. So you can see we've got like 16 studies that just have a single estimate, maybe what, about 17 or 18 that have two estimates, and then a couple that have between 3 and 8 estimates. This is pretty, I think, pretty typical of the amount of multiplicity that you might see in a meta-analysis in psych or in education. Here's the same thing in the narrative assessments review. You can see that there's like a bigger range of multiplicity. So in the bottom left here, right, there's just a couple studies that have just a single effect size estimate. Many have like 3 to 8. And then there's right, a couple that have over a dozen, even one that has, I think, 43 different effect size estimates in it. So right, the imbalance from study to study and how many estimates you have is going to be important. It's going to play a role in how sensitive your analysis is to the model that you choose. If all of the studies had the exact same number of estimates, you could almost fit any model you want and you'll get very consistent results. But with data like this, depending on the model that you use, that can sort of shift how evidence is weighted. The other complexity to the narrative assessments review is that some of the included studies reported results from more than one sample. So on the right here, I've just got a sort of histogram of how many samples per study were included. So there's one study that is based on 3 distinct samples. A couple have 2 samples, most just have 1. And that'll, again, sort of add complexity to the complexity and sensitivity to modeling assumptions. So it's important to know that at the outset. The other thing that's useful to look at here, I think, is just the distribution of sample sizes of the included studies. Again, like if all of the studies had a very similar sample sizes, you could fit almost any model that you like. And the results will generally be very robust to different modeling assumptions. The more variation in modeling, in sample sizes there is in this set of included studies, the more sensitive the results will be to specific modeling assumptions. So to visualize this, I've just used like a density plot of the total sample size of each of the included studies. In the Spiritual Well-Being Review, there's fairly wide range, right? So some of the studies are quite small, like just a couple dozen, up to maybe 150 or so. And then there's a couple of studies that have over 200 participants, 2 that have over 300. So these are right big studies that are going to tend to get more weight in the analysis and will therefore be influential. And I should have said, the hashes down at the bottom of each of the density plots represent like the individual observations. And then the blob is just a kernel density estimate of the distribution. On the bottom, the distribution of sample sizes in the narrative assessments review is even more sort of imbalanced, right? Almost all of the studies have less than about 75 participants, a couple with over 100, and then there's this one giant study with over 400 participants that's going to end up being sort of like a beast, right? It takes a lot of the weight in the meta-analysis because its sample size is so much larger. The other thing that there's other sort of question that you might ask with this sort of display is whether this the question that comes up for me at least is like is there something goofy about this big study? Like is there a reason that right almost all of this literature is with sample sizes under 100, but then for whatever reason there's this one that's 4 times as large. So checking that this big study sort of really does fit inclusion criteria, or understanding whether it's sort of categorically different from the other studies in some way, I think is a useful thing to do that's prompted by looking at this sort of graphic. Stage two, looking at study characteristics, just like sort of descriptive characteristics of the included studies. And then many times those descriptive characteristics serve as the basis for moderation analysis. So we can think of, I sort of think of study characteristics and potential moderators as the same category of variables. Here, the questions that we're trying to answer are basic things like what's the distribution of these characteristics across the set of included studies? How completely are the characteristics reported? That we know in practice, oftentimes a lot of the information that you would like to have about studies might go underreported or be incompletely reported. And then how are those study characteristics related to the dependence structure? Answering these questions is useful just on the basic level of checking that the data are right, checking that the data, like the codes that you're using are consistent with the operational definitions that you specified at the earlier stages of the synthesis. Then thinking about whether after the screening and coding process, maybe some of the categories that you started out hoping to analyze are not sufficiently populated, right? Maybe there's only like 2 or 3 studies that include a particular level. So looking for sparse categories and then thinking about what to do about them is a useful exercise at this stage. And then thinking about the dependence structure specifically is useful for identifying more specifically how you'll go about doing moderator analysis. If there's within study variation in the moderator, that suggests certain opportunities for analysis that might not be available otherwise. So I'll give you a couple of illustrations here. In the spiritual well-being review, there were a bunch of study characteristics, things like aspects of the participant sample, like this, it was all cancer patients or survivors. So the stage of cancer, the specific class of intervention that was examined, the type of outcome measure that was examined, and here you can see the almost or the vast majority of the included studies used this one particular measure of spiritual well-being from it's called the Facet SP instrument. So 27 out of the studies, total of 61 effect sizes, all use the same instrument. And then a couple of the other instruments that reported in some studies were really sort of one-offs, right? So like this body, mind, spirit, well-being inventory, the expressions of spirituality inventory, right? These are reported in very few studies. So the question that might come up at this stage is, can we really sort of analyze the data by outcome measure? And if so, right, do we need to like lump these different sort of unusual outcome measures together somehow? For continuous moderators, things like density plots might be useful. So for example, here's like the average age of the samples in each included study. So the 40 out of, I think 40 out of 41 studies reported this. So that means 2.4% of the data are missing. Here's the proportion female. So it ranges from all male to all female. Most of the studies are a mix, but there are a couple of studies that have nearly 100% female samples. Um, and these are actually, right, drilling into this, we find these are mostly breast cancer, like studies that were specific to samples of breast cancer patients and survivors. So that sort of makes you think about, well, the interpretation of this particular study characteristic and whether we might have to think about other things if we're trying to understand variation in effects based on the proportion female. Here's one more. This is the distribution of the number of intervention sessions used in each of the studies. So in most cases, the interventions were fairly brief, between 1 and 12 intervention sessions. But then there's this one outlier that was a much more intensive intervention. So where a plot like this might help you identify this outlying value of the study characteristic, right? Would raise questions about, is there something else that's weird about this study? I mean, is this value even right? Um, and if you were hoping to use number of sessions as a predictor in the model, do we really want to use this study, right? If we do, this is going to be a very high leverage, very influential observation because its value of the predictor is so different than everything else. So these are just sort of what I would call marginal descriptives, looking at one variable at a time. The other thing that I think is useful to do is look at the hierarchical structure of study characteristics. And we suggest a couple of different techniques for doing this. Uh, for a continuous variable, one thing you can do is just plot, uh, we call it like a range plot. So show for each effect size in a given sample. So samples here is on the vertical axis. What is the range of the continuous predictor? So this is weeks from baseline at which the outcome was measured. So this is a within study characteristic because many of the studies measured the outcomes at multiple points in time. You can see there's one that just did an immediate follow-up, and then a bunch of studies did follow-ups between like 4 and 12 weeks or so. And the range varies, but there's a fair amount of within study variation in this predictor. So if we were interested in understanding, right, variation in effects based on the duration of follow-up or the weeks from baseline, we could use this within study information, and maybe we would use it separately from the between study information. Because those give us sort of different angles on the question, right? The within study information is sort of holding the other study characteristics constant, whereas if we're looking between studies, we've got to worry about other differences between the studies. So I think plots like this, they kind of look like forest plots almost, right? In that there's like a row for every sample in the database, but it's just the horizontal axis is not the effect size estimate, it's a different value. This is, I think, is useful for continuous characteristics. For categorical characteristics, it's a little bit harder to get at the dependency structure. So one sort of table that we've suggested is what we call a dependency table. So for a categorical variable, like say the class of intervention in the spiritual well-being review, you can look at the distribution of the number of studies. So that's the initial number here. And then the number of effect size estimates that co-occur for every combination, like every pair of possible intervention classes. So like this number here, the one study with 3 effect size estimates, this study included an intervention that was in the category of meaning or existential. And it also included a separate intervention category that was skills-based or CBT, right? So this says, right, this study has both types of interventions in it. And there's, right, this one other instance where you've got 2 studies that have both an education or healthy lifestyle behavior intervention and a meditation or yoga intervention. So for these studies, you could do the within study comparison of like meaning existential versus skill-based or CBT. But for the most part, there's not a lot of data on these combinations of different categories of intervention. So the opportunities for like within study analysis of different intervention classes is pretty limited, right? We wouldn't be able to do much of like a network meta-analysis here because there's just not enough data on the different combinations of intervention classes. Another illustration of this from the narrative assessments review. So in this review, they categorize their assessments by type. So there's 4 types: ISL, macrostructure, microstructure, or mixed. And here there's more like data in the off diagonals. Like here we can see there's 22 studies, 33 samples, 153 effect size estimates for the microstructure outcomes that co-occur with macrostructure outcomes. So if we wanted to sort of understand differences between macro and micro, we could use this within study information to look at the differences between those 2 categories. It's less feasible to do for the other categories because there's so many fewer studies look at the other like combinations of assessment types. But at least for this one, maybe we could drill in and look at like within study variation in macro and micro. These plots are these tables are a little bit tricky to compute, but Jingyu put together like sort of complete workflow documents for all of the examples, and we've shared those documents with in the supplementary materials of the paper. And I think Jingru can correct me maybe, but I think we've got like a function in those data sets or in those scripts that does a table like this, just spits it out. You feed it in a variable and like the study IDs, and it sort of constructs this table for you. So this is just sort of a sample of the different study characteristics or the different sort of descriptive analysis that you might do of study characteristics. Other things that might be useful to explore and that we illustrate in the full paper include like looking at the multivariate structure of the characteristics, trying to understand how correlated different predictors are using things like scatter plot matrices or even like cluster analysis of the studies. And then also looking at missingness rates and the structure of missingness. Jake Schauer and Jihun Lee and some of their collaborators and Terry actually too, have some good work specifically on how to do this for meta-analysis. They sort of describe like a preliminary data analysis workflow specifically around understanding missingness in this paper here. Stage 3, looking at standard errors and other auxiliary quantities. So now we're moving a little bit more towards the technical. So questions to ask in this stage of the workflow would be just what is the distribution of standard errors marginally? And then to what extent do standard errors vary within studies? And this is useful for a couple of reasons. One is just checking the accuracy of those standard error calculations. Right, we all know like this is an error-prone area of meta-analysis. It's pretty easy to get a standard deviation confused with a standard error, leading to like wildly different, wildly inaccurate, right, assessments of the uncertainty in the effect size estimates that can create like very influential points. So it's useful to be very careful and diligent in looking at these standard errors. And the other thing that this lets us do is get a sort of further initial sense of how weight is going to be allocated in like a summary meta-analysis. There's one complication here. For some Well, the exact way you proceed here depends on the effect size metric that you use. So for standardized mean differences measured across multiple outcomes, for like Z-transformed correlation coefficients measured on the same sample, the effect size estimates that are drawn from the same sample should usually have very similar standard errors. That's not true of some other effect size metrics, though. And there's a further wrinkle with standardized mean differences that the standard error that you compute for meta-analysis is is going to be is going to vary within study because of the correlation between the effect size and its standard error. So we suggest like computing like a modified standard error, what we call a scaled standard error, that removes this correlation and that should therefore remove some of the within study dependence. This is sort of like removing the within study variation that we know is just an artifact of this correlation. The way you would compute this is to take the squared standard error that you compute and then pull off the part of that standard error that is that creates this correlation, the part that has to do with the effect size estimate itself. So that part is the squared standardized mean difference estimate over 2 times the degrees of freedom that go with that effect size estimate. So degrees of freedom, like right, sample size minus total sample size minus 2. So using this scaled standard error, you should typically get standard error, these very little variation within a given study. Here's a plot of this for the narrative assessments review. So this is again kind of like a forest plot, right? There's a row for each sample. And then, but instead of plotting effect size estimates, we plot standard errors. These are the raw standard errors. So you can see there is a little, like there's some within study variation, like in this Newman and McGregor study, right? There's like the standard errors vary from like 0.45 up to 0.65 or so. And that happens in a couple of other studies as well, right? Standard errors above 0.5, to me, this is like the reason to be curious, right? A standard error of 0.5 means usually a very small sample, like under a dozen. So it's good to sort of follow up on those. Here's the same plot with the scaled standard errors. And you can see, right, this actually it removes all of the within study variation, right? So you get standard errors that are nearly identical within a given sample. And that's a sort of a good sign, right? It's a sign that there's nothing too anomalous about the standard errors that you computed. It doesn't guarantee that they're right, of course, but it gives you some assurance. The other thing we can do at this stage is look at the weight distribution. The right the exact weight distribution in like a summary meta-analysis will depend a whole lot on what model that you use. So right, in particular, because right, you're going to estimate between study variance, maybe estimate within study variance as well, and those variance components are going to go into the weights. But as a preliminary thing, we could think of like a very simple model, a model that doesn't have any sort of variance components, no heterogeneity in the effect size estimates, where we're just weighting the effects based on their sampling covariance matrices. We call these inverse sampling covariance or ISC weights, and they're a fairly simple function of the squared standard error, the number of effect size estimates in a given study, and then the correlation between the effect size estimates, which I've denoted here as rho. And oftentimes we just have to make an assumption about this correlation, and we might sort of wiggle it up and down. But we can compute these weights for a couple of different correlations, and then see right what the implication is for which studies get a lot of weight and which studies get less weight. Here I've plotted this for the narrative assessments review, and the different colors correspond to different assumptions about the correlation. Big thing that jumps out of this is the Kapazoglu study gets a whole lot of weight. It gets like 12+% of the weight out of 40 some samples. And all of the other studies get like under 3 or 4%. And most of those other ones, they get a fairly equal allocation of weight. But Kapensaglu is like a big outlier. That's because this is the study that has the giant sample size. And so, right, it has much smaller standard errors, therefore it's going to get a much bigger weight allocation. And looking at the sort of the variation in the weight allocation across different assumptions, I'd say like there's not a whole lot of wiggle in this. So it suggests that, right, using different assumptions for the correlation probably won't affect the weight allocation all that much. So hopefully won't affect the summary meta-analysis results to a great deal. This is just a taste of like the statistics that you might look at in this stage. Again, it depends on the metric that you're using. Like if you're looking at correlations, you might look also at like Cronbach's alpha coefficients or retest reliabilities that you pull out along with the focal correlations. If you're looking at standardized mean differences, like D effect sizes, you might look at the distribution of standard deviations. Like in the spiritual well-being review, many of the studies use the same instrument. So understanding the degree to which the standard deviations vary from sample to sample is kind of interesting. For binary outcomes, you might look at the distribution of baseline risk levels because that will sort of affect the choice of effect size metric, like using an odds ratio versus a risk ratio. Last stage, and I know I'm sort of bumping up against time here, is to look at the distribution of effect size estimates, right? So these will be like the focal dependent variable in your analysis. And again, we're interested in what's the distribution and what is the hierarchical structure for mostly the same reasons that we're interested in standard errors, right? So basic thing would be to check that the effect sizes are accurate, for instance, that the valence of the effect size is coded the right way for the particular outcome that you're looking at. It's useful to look at the distribution to identify potential outliers, and then also to inform the potential models that you might fit to the data, right? Looking at how the effects vary within and across studies is sort of informative for understanding different sources of heterogeneity. This is this stage of the preliminary data analysis where there's sort of the most convention already available, right? People, I think, often will look at just like a scatter or like a histogram or a density plot of the effect size estimates, and then things like forest plots are helpful here, and those are well understood, widely used. So here's an illustration of just the marginal distribution of the effect size estimates in the narrative assessments review. You can see it's quite a wide distribution. At the bottom, I've just aggregated the effects up to the sample level to get a sense of like sort of between sample variation, which is also wide. And this sort of thing you might use to do like, look for outliers, maybe do Windsorization of big outlying effect size estimates. I've represented the fences for Windsorization using these dashed lines, but there were no outliers by sort of conventional criteria here. So forest plots are sort of a standard tool. They get a little bit hard to construct if you have like many studies or especially many effect size estimates from a set of studies. So one technique that I think might be useful here is to do like sort of a hierarchical forest plot where you've got a row for each sample. And then if you've got multiple estimates, multiple effect sizes from a given sample, you plot them all kind of in a cloud on that line. So these are the effect size estimates from the narrative assessments review. Right, the forest plot here gives you a sense of like the overall variation in effect size estimates, but then you can also look at specific studies and say, for instance, oh, Newman and McGregor, what is the deal with your two effect size estimates here that are so discrepant from all of the other estimates in that study? Even though they're not necessarily outliers in the overall distribution, there may be outliers in the within study distribution. And plots like this also sort of raise questions about is the degree of within study variation kind of consistent from study to study? A lot of times the formal models that we would use for this sort of thing make that assumption. And so looking at plots like this can sort of lead you to ask questions about whether that assumption is reasonable. So let me wrap up. Right, the big picture here is that, right, even outside of meta-analysis, any sort of statistical analysis that we do, the validity of the conclusions that we draw, the inferences that we make on the basis of a statistical model depend on, first, having accurate, right, input data, and second, having sound modeling assumptions. And we think that doing this sort of preliminary data analysis is gives you useful insights to improve on these things, right? To ensure that you've got high integrity, accurate data, and that you will, when you move to the stage of doing formal analysis, be making good assumptions. So we propose this primed workflow as just a description of what we see as useful preliminary data analysis procedures specifically for meta-analysis, and really specifically for meta-analyses involving dependent effect sizes. We expect it's probably going to be most useful for bigger projects, like larger databases of studies that tend to have more heterogeneous features and where dependency is sort of a central feature of the data. Right, this is probably overkill if you're doing a very focused meta-analysis with just a handful of studies in it. But I mean, right, meta-analyses tend to be large, right? They tend to have dozens of studies in them, oftentimes scores of effect size estimates. And right, that sort of thing is very common in education and in many other disciplines too. I want to emphasize, right, our primed workflow is really meant to be like a scaffold that you can build on. It's not meant to be like a complete, sufficient procedure to follow by the letter. It's really meant to be more like inspiration for doing this type of analysis, right? So we would encourage you to sort of, take what you find useful from the workflow that we've described, apply it to your own practice, but then also, right, look for other useful descriptive tables and descriptive graphics and share those things with the community. Right, so this is, I think, I would love if this paper were like the start of a conversation about this rather than the last word. And there's certainly a number of sort of outstanding questions about this sort of thing. I think one very pragmatic one would be, it seems like there might be ways to kind of somewhat automate construction of this sort of preliminary data analysis. I wouldn't want to automate it completely because that works against like the spirit of like tailoring the analysis to the features of your data, right? Making this so turning the scaffold into a complete picture of giving your research project, giving your aims. But maybe there's ways to sort of speed things up, make it easier to generate graphics and generate tables. Another question is, well, what do we do with this stuff then? Like, should these sorts of graphics go into manuscripts? I would think they will mostly be things that could be shared through supplementary materials, but it sure would be nice if people shared them, even as supplementary materials, right? It would give readers further insights into the structure of the data. We put more eyes onto the data that could help the community identify sort of useful follow-up analysis or maybe raise questions that are not obvious from the analysis that's presented in a manuscript. I think there's also big open questions about how to build this sort of preliminary data analysis workflow into a pre-registered process. Oftentimes people, right, especially for large reviews, they will pre-register um, their aims, maybe even pre-register specific analyses that are to be conducted. And the preliminary workflow tends to be more exploratory. It seems like it should inform later data analysis, but that kind of works against the idea of having a pre-registered analysis, or at least there's some tension there. So I think we need as a community to have a conversation about how this would all kind of fit together into the aims of doing uh, pre-registered projects, and also the broader aims of having like a transparent and replicable science of systematic review and synthesis. I'll leave it there with another link to the preprint, and I'm happy to take questions and have discussion about this.
Wow. Thank you so much. There was a lot in there that is super exciting. It makes me feel guilty for not examining my data this thoroughly, descriptively before running analyses. But wow, the potential to really do it in a more rigorous way is really exciting. So thank you, James. Yes, we do have some time for questions. I know there's a little bit of commenting, mostly my silliness on the chat, but there's also some serious
Yeah, I'm
comments
looking at this.
on the
Yeah,
chat as well. But other questions you could ask on the chat, or you can unmute and voice them as well. So
Carlton, which was the figure that got you all worked up?
it was that last one, the one, the
Oh,
like
the
forest plot like 3.0. Like it just was
uh,
so
yeah,
good. Yeah, to see the variability of the dependent effect sizes like within the forest plot. I was just like, whoa.
yeah. Jingru really pulled out all the stops and like working out how to make this look like capture all of the features that we want in that plot.
Okay,
I
we have
see a
Noah,
question from
I think.
Noah.
Yeah.
Hey, James, thanks for this presentation. I think this was an awesome reminder of all the things we should be doing rather than what sometimes we may overlook. As you were showing the things about the dependent structures, it reminded me of your paper from a few years ago about expanding the range of working models. And I was wondering if you also see the connection between that and choosing different types of working models and how these types of graphs can help you choose that. So I guess what I'm asking is, if you agree, could you talk briefly about how these can help you choose the right working model? Because I think for people who might not have read that paper relatively
Yeah,
recently, it might not be really apparent why this is relevant. And it's a good reminder for me too. And thank
yeah,
you.
yeah, yeah. Great question. Thank you, Noah. Yeah, yeah. This, I mean, that those types of models were definitely on my mind as we were developing this material. I'll highlight two things. So one is like in this hierarchical forest plot, for example, the assumption of so in our earlier paper, we suggest that like maybe a sort of a baseline working model for dependent effects would have what we call the correlated and hierarchical structure. So the correlated part has to do with the correlation between the effect size estimates, which is a little bit hard to see in these tables. The hierarchical part, though, is right, I think pretty clear, right? Like there's variation within studies or within samples here in the effect size estimates. And then there's variation between studies. And we can pull those two things apart using the correlated and hierarchical model, or really using any sort of hierarchical meta-analysis model. But right, the one of the assumptions of those sort of hierarchical random effects models is that the degree of within study variation is consistent across studies. Right. So the within study variation in, say, Norbury and Bishop is the same, or we're modeling it with the same degree of variance as the within study variation in Hoffman and the within study variation in Newman and McGregor and right Rosanico et al. So plots like this oftentimes make me worry about that assumption, right? Make me question it. And I don't have a great answer at this point about like what you would do if you're worried about it, other than maybe, right, maybe there's some further analysis that you would do after you've started formal modeling to check whether the model that you're using sort of seems consistent with the data. Um, the other thing that one other way that this sort of preliminary analysis might inform your modeling decisions is um, in the earlier stages, like when you're looking at study characteristics. Uh, Here we've got right, a breakout of like the dependent structure of several different study characteristics of several different assessment types. This is like an effect level or like a within study characteristic. You can think of these as different outcomes, right? Different categories of outcomes measured within a study. So if you've got this type of structure, like within study variation in outcome types, and if you have many studies that measure multiple categories of outcomes, you can think about doing multivariate working models, right? We could, for example, allow for the variation in effect sizes for ISL to be different from the variation in macro, to be different from the variation in micro or mixed, and then also allow for correlation between like the study level average effects for macro and the study level average effects for micro. So you can move more towards doing a multivariate model, but doing that requires that you've got like a lot of that this full like contingency table is populated, right? That there's a lot of information about the different combinations of assessment types or whatever your outcome categories are. If you don't have that, like in this example down at the bottom, then those sorts of multivariate working models are not going to they're not going to be feasible. There's no point in trying to fit them because there's just not enough information in the data to get decent estimates.
Awesome. Thank you.
Yeah, did you have other thoughts on that question?
No, not really. It was more just like I was thinking about that paper and like with some of my students I find that it's hard to connect the concepts without the numbers sometimes and these graphs add numbers to the concepts and I kind of liked that and I think you elaborated on that perfectly. Way better than I would have because I would have talked for 45 minutes to say what you said in two. So
Yeah.
I just wanted to say thank you.
Yeah, could I ask you, so you had some comments in the chat about like the tooling or semi-automation.
Yeah.
Yeah, could you say more about that?
Oh yeah. So as you were walking through these steps, if it's formalized, I apologize if you can hear my dog going bonkers in the background.
You're
She's
good.
okay, good. Because it's hard to concentrate. So the I was thinking that you could basically build a GUI that you can upload your file and then it'll run through all of the steps of the process with essentially every column where you could specify the columns. I think there's 99 different ways to do it per se, but I
Yeah,
think
sure.
one could build a Shiny app that runs through it essentially in an automated fashion, and then at each step have I conceptualize things as like core requirements. Like if you do a meta-analysis, obviously you're going to calculate your overall effect size and you want to know your heterogeneity. So those are like core things to me. But then different types of publication bias analysis, for example, might be supplementary or like things that you choose to do. Like maybe you prefer one test over another. So with
I
this
see.
process, I was thinking that you could make the core functionality as an automated thing, and then basically have drop down menus for each step of the. I think you said it was a 7 step process, and so you could have each one have those kind of supplementary things that like if you see something that's a flag to you, like the dependent structures or whatever, you could then dig down farther. But the challenge with it is it's kind of a never ending task, I'd imagine, of
Yeah.
infiniteness. And so that's kind of, I only thought about it briefly as you were presenting this, but the short version is I think you could build a Shiny app without too much headache to do the core stuff. And
Yeah.
then how far down the rabbit hole you really want to go is kind of up to you. But
Right.
that kind of what I was thinking is, if you upload your file in the beginning with a specific format, it could run through all the core things for you.
I think it'd be pretty cool.
Yeah.
Like a metadata explorer almost.
Yeah, yeah. And I mean, some of the LLMs are really, really good at first draft of shiny stuff. So as I was looking at, I was trying to pull open your code, but I got distracted by an email. I think if you put your base code into like an LLM, it could probably do a first draft that you could then go through and proof to make sure it's actually, doing your
Right.
computation right and things like that. In theory, it wouldn't be too hard, but I'm also one of those people who like sits down. I'm like, in theory, this won't be hard. I'll get it done in half an hour. And then, 3
10
a.m.
hours later.
Yeah.
Yeah.
I'm still like, I should probably go to sleep.
Yeah.
So yeah, that's all I was thinking about. I'm happy to chat about it offline with you if you want to do something like that. I
Yeah.
don't,
Yeah. Cool. Thanks. Thanks for sharing.
yeah, thank you.
Wow. Well, thank you. This is great. I'm excited for yeah, just what you shared and all the all the next steps for this. This is really cool. So, I do want to, I know we are over, so I do want to officially wrap it up. And, I think James potentially could linger a little bit if there's other conversations, but I do want to thank everyone for coming once again. And we do have another webinar next month, and that's Marta Pellegrini and Terry Pigott together. So they'll be co-presenting on some recent work evaluating the methodological quality of educational meta-analyses. So another, I'm sure, really great talk that Yo will all want to join us for. So please join us for that as well. I do want to do a quick plug that I forgot. We do have our AERA submissions all reviewed, and our program chairs are busy making those decisions as well as compiling the sessions together. So we should be hearing AERA decisions around early November, I believe is what they're saying. So stay tuned for that. But other than that, have a great Friday and weekend. And thanks again so much to James. So